In the last video, we saw a definition for point of inflection, which is a spot in the graph of a function where concavity changes and there is a tangent line. We also saw the second derivative test for concavity, which says I get the concave up shape on intervals where my derivative is positive and a concave down shape where my second derivative is negative. So, in this problem, I'm asked to determine concavity and find inflection points for this function. So, let's take two derivatives and see if we can do that. So there's my first derivative. That would help me find out places where my graph increased or decreased, and now a second derivative. And this is going to help me figure out where my graph is concave up and where my graph is concave down. I'll summarize that by drawing a little number line. By setting the second derivative equal to 0, I find where I'll get those nice spots where I might change from a positive to a negative. And if I really think about the definition of a point of inflection, I have to have a tangent line, but it might be vertical. And my concavity needs to change. It means I'm looking for places where my second derivative might change sign, which is either going to be where the second derivative is 0 or where it doesn't exist. So what I'm really doing is thinking about critical points. We don't call these critical points because they're actually critical points of the first derivative. But on my number line here, I put any place where the second derivative is equal to 0 or does not exist. All right, on the left-hand side of 1 here, I can imagine plugging in a 0 and getting out a -6. So on this interval, my second derivative is negative. On the right-hand side of 1, I can imagine plugging in a 2 where I'll also get it, well, I'll get out a +6 where my second derivative would be positive. All right, so concavity. I will be concave down on this interval from -infinity to 1 and concave up on the interval from 1 to infinity. The problem also asks me to find an inflection point, if one exists. Well, my concavity changes at 1. So the x-coordinate of my point of inflection must be 1. I have to use the original function to find the y value. But first, let's check that other requirement. Concavity has to change and I have to have a tangent line. Well, the first derivative exists at 1, which means when I plug 1 in, I get a slope. Well, if I get a slope, that means a tangent line of that slope exists at that point. So I'm good. I have a tangent line. Now, I should be careful because I'm not saying I only have a point of inflection when the first derivative exists, because of that case where I do get a point of inflection when there's a vertical tangent line. But I'm absolutely sure I do have a tangent line when the first derivative exists. All right, let's plug 1 in for x and find that y value. 1 minus 3 plus 2 is 0. There's a point of inflection at 1, 0. All right, we have found the intervals of the different concavities. We have found a point of inflection at 1, 0. And we'll have more examples following this one.